Okay, so for today's class, this is mainly it's technically mainly going to be review. There's only a few things that are going to be new that we talk about. So this is going to be, we're going to basically start a chapter on ethers. So remember, ethers are basically carbon, oxygen, carbon, and I'll put a star there, or a prime, so it's two different carbons. So these are relatively inert. It's a relatively inert functional group, and we use ethers as solvents. So the two which we have used the most are THF, which is a cyclic ether, tetrahydrofuran, and the other one is diethyl ether, which looks like this. So they're both really common aprotic solvents. Diethyl ether's got a relatively low boiling point. I think it's around 35 degrees. So on a summer day, it's actually, it'll start to evaporate quite readily. And you use this, I believe you use this when you're doing your Grignard reaction. So you've used it before, and yeah, so they're the most common solvents. So at the end of organic one, like how to make ethers. So how to make at the end of organic one, there was a method that we used. And I guess the technical name for this is Williamson Synthesis. So we would take our alcohol, we would react it with sodium hydride. This would generate our plus molecular hydrogen, which would boil out. Then we would add an electrophile, so our X equals chlorine, X equals bromine, X equals iodine. And we would have our product. So this was what we did at the end of organic one. Now there's some strict conditions that are placed upon this sort of reaction. And that is that during the second step here, after we've deprotonated, so this step, step 2, the key point here is that this reaction is SN2. So we've got strict limitations on what our primes can be. So because it's an SN2 reaction, R primed is, it really should be methyl or a primary alkyl halide. Secondary alkyl halides, you can have some problems. Tertiary alkyl halides, you are going to have basically a disaster. what is the disaster which can take place, and what are some of the problems that could take place if you try this on, say, or, oh, I guess I'll just leave it like this. What are the problems we're going to get if we try this reaction on like tert-butyl bromide or 2-iodo-butane? What would be some of the potential products, the potential issues we would have here? The problem is going to be E2 elimination. So remember that if you've got a depending upon what your R group is here, you can have all sorts of elimination issues. So in the case of a tertiary alkyl halide, you are going to remove one of these protons really quickly. Boom, boom, boom. And what you're going to end up with, your two products are going to be you're gonna just basically return to your alcohol. So with tertiary alkyl halides, this is never going to work. So you can't use this synthesis on a tertiary alkyl halide. With secondary alkyl halides, the competing E2 elimination reaction becomes quite significant. And depending upon what your R group is, there's two different reactions which can take place. You could have sort of a Hoffman or a Zetsiev elimination reaction. You can make this, or you could do this. So it's a problem. So this Williamson synthesis, ether synthesis, really works well with primary or methyl alkyl halides. So if we had, say, for example, this case here, we would make our methyl ether. What would be another example? We could make butyl ethyl ether in this case. So these would be relatively reliable reactions. We use sodium hydride as our base. Remember, so sodium or potassium hydride would be the base because we want to make certain that, come on, erase. We want to make, this reaction is irreversible. So it's going to deprotonate and you're going to have sodium floating around in the reaction, basically as a spectator ion. But your hydrogen gas, this is going to bubble out of the reaction. So this makes this process irreversible. And remember, hydride is basic enough that it is going to grab that proton and yeah, it's going to bubble out. So it's completely irreversible. If you use something like sodium hydroxide, the pKa between an alcohol and water is too close, and that's going to, so if you tried the same thing with, say, sodium hydroxide, this is going to be an equilibrium process, and that isn't going to be particularly helpful for what we're trying to do. The pKa of water is too close to the pKa of the alcohol. So it's an equilibrium. And when we're deprotonating our alcohol, we want it to react. So we want this to be our reactive group, not hydroxide. So we always try to do reactions in which it completely converts our alcohol and deprotonates it. So sodium hydride or potassium hydride are going to be our go-to reagents for anytime we want to deprotonate an alcohol. Now, so Williamson synthesis can be used to make ethers that can be composed of if it's got using a methyl halide or an alkyl halide, primary alkyl halide. But what happens if how would we make something like this? And let's say that you have which of the two do we want to use? Let's say we have ethanol as our alcohol to work with. How would we make that? So the Williamson synthesis isn't going to work because if we're breaking this bond here, the you can't have that tertiary group is going to be eliminated too quickly. So we can't use that. The good news is that there's a reaction that we've done at the start of this term, which can be applied to ether synthesis. So we already know how it works. And that is basically the Oxy Mercuration reaction. So in a case like this, what we would do is we would start with, so if we have a tert-butyl, if we want to like have a tert-butyl group, if we're making this, breaking this bond here, we basically need an electrophile in which the positive charge is on that tertiary carbon here. Trying an SN1 reaction for this might not be the best option because SN1 reactions, there can be a competing elimination reactions. But if we do an Oxymercuration reaction, we don't have to worry about that. So an Oxymercuration reaction, it starts with alkenes. So we would take this this alkene, we would react it with our mercury, HgOAc2. 2. And our solvent is going to be the alcohol we want to react it with. So we would have ethanol as our solvent. Sometimes this would be mixed with THF, just to dissolve everything. And this will make and if we don't remember that part, we'll just do that in a second. Then the second step, of course, would be our reduction with sodium borohydride, pH4. And that will make our final alcohol. So just as a reminder for the mechanism of this, we've got our alkene, got our mercury, remember our alkene is going to be the nucleophile, attack the mercury, acetate leaves, then the mercury's lone pairs are going to I'll draw that in purple. And we're going to make our mercurium ion. Plus. Now we have our solvent, which can attack this mercurium ion. And of course, remember, it attacks the most substituted carbon on the opposite side because this bond here is weaker than the other bond because this positive charge is basically shared between the 3 atoms, and the atom which can stabilize it the best is that carbon, is this carbon here, because it's best able to stabilize a delta plus because it's got all of the alkyl groups donating electron density inductively, or it could stabilize it through hyperconjugation. So that carbon's got the largest delta plus. So alcohol attacks, those electrons move up. Then we have a little intermediate here, which looks like this. And the proton on the what will become the ether, this just gets removed by that. You can remove it with the solvent, or you can remove it with the acetate anion, which left originally right here. And this will come along and grab proton. You can use ethanol to deprotonate it too. And that gives us our intermediate, which will then later get reduced. So this will give us do I have a question somewhere? No. Oops, that's not right. There's ether. So then later on, this group will be reduced with the sodium borohydride. So the oxymercuration is a really nice way of making ethers, which would normally be very sterically hindered. So there's 2 complementary strategies for making ethers. And we've seen them both before. So sodium borohydride, for very simple ethers which have got methyl groups or primary groups. And for secondary and tertiary, the better route is using the Oxymercuration reaction. So if we had something like this, and we did this, then our first step product would look like, in this case, they're both the same. 1, 2, 3, 4. And then we would reduce off that mercury, and voila, we've got this very nice. Maybe I'll make it like that, so it's a bit more sterically hindered there. And then we would have this very complex ether, and actually this would be no longer down, we just consider it straight. So the key point, though, is that, let's do another one just for the sake of argument. First step, mercury diacetate in the presence of ethanol, THF. Second step, sodium borohydride. So we're going to put the oxygen on the more substituted carbon. So we would generate an ether that looked like this. So out of carbon A or carbon B, oxygen is going to attach to carbon A because it's more substituted. And so this is a relatively complex ether here, and we're using two of the groups that we've got a lot of chemistry for, the alkenes and now the alcohol. So yeah, those are the two main ways of making ethers that we've sort of seen before, but now we're just seeing in a bit more detail. So oxymercuration with an alcohol as the solvent will make ethers, or we can use Williamson synthesis, which is basically an alcohol, deprotonate it with with sodium hydride, and then react it with a simple alkyl halide, and you'll make your ether that way. So those are the two main ways to make these. There are two new reactions that I should show you. But just as a slight review, we have seen another ether in action before, and that, remember, is an epoxide. So remember, an epoxide is 2 carbons and an oxygen in a 3-membered ring. And we make epoxides. Sure, okay. Let's do a couple of reactions here. Okay, so I'll just move this out of the way. Okay, so everyone, we'll do a couple of practice questions here. Okay, so everybody take a couple of seconds and try to do these 3 reactions. So all of the products should be ethers. Mm-hmm. Okay, does everyone have an answer for some of them? All right, so in the first step, okay, sodium hydride is going to deprotonate our alcohol. So in the first 2 questions, that's the first step. We're deprotonating our alcohol to make our nucleophile. And in the second step is technically the, so all this guy here will be the electrophile. Okay, so we start with 1, 2, 3. 1, 2, 3. 1, 2, 3. Oxygen, and then it's going to be bonded to our ethyl group, which of course is 2 carbons, 1, 2. And we have cyclohexanol that will be deprotonated, and that oxygen is going to attack the methyl group. Iodine's going to leave, and so we will make the methyl. So just draw it as a other way of drawing this, of course, would be or same thing. Now in the third example here, we've got an alkene. And so one of the carbons is more substituted, i.e. the one in the orange circle. So that is the one which is going to be attacked by the alcohol. So in this case, this is the nucleophile. And the mercurium ion is the electrophile. So the sodium borohydride is just going to get rid of the mercury. So what we're going to have here is that this will be our product. So let me label the carbons. Pink. A, B, C, D, E. A, B, C, D, E. So the most substituted carbon is bonded to the oxygen. And then the 1, 2, 3, 1, 2, 3. So relatively complex ether, and we're using mercury to make that more substituted carbon the electrophile. Way more reliable than trying to do an SN1 reaction on it. Way more reliable. So that's why you don't really see SN1 reactions being attempted that much with this sort of stuff. Because of the mercury, there's very little side reaction. So that's basically the way that this works. So in each one of these cases, either the deprotonated alcohol, so the alkoxide's the nucleophile, or in the third example with mercury, the alcohol's the nucleophile. It's just the electrophiles are changing and the type of reaction is slightly different. So this will be SN2, SN2, and this is a oxymercuration basically mechanism. Okay, the other ether that we did see was the epoxide. Actually, before I do that, were there any questions on any of these? How did you do? Excellent. Okay. Now the epoxide. So we know how to make epoxides by MCPBA, right? So alkene plus MCPBA goes to epoxide. So for example, my favorite example. So MCPBA is that peroxybenzoic acid. So if we do this, we are going to make our epoxide, and I'll just draw the stereochemistry up. It would be 50% of it would be up, 50% of it would be down. But for the next part, the important part, we need to just at least define one way or the other. So remember with epoxides, we talked about opening up epoxides basically under two different scenarios: acidic or basic. Now, the general rule is that under acidic conditions, the nucleophile will attack the more substituted carbon. So we view the epoxide, the protonated epoxide, essentially the same as, so if you had that under these conditions, your nucleophile will attack the more substituted carbon exactly for the same reasons why it attacked it for the oxymercuration. So, and under acidic conditions, these nucleophiles will essentially be neutral species. So these nucleophiles will be things like water. That's probably the best example. So making an epoxide and then reacting it with H3O plus in water would give us a transdiol. So, but if I label this carbon in orange on our product, the orange carbon, the orange oxygen is this one here, because it's attacked the epoxide on the opposite side on the more substituted carbon. So this methyl group would technically be inverted, and that nucleophilic oxygen is going to be on the more substituted carbon. So with under basic conditions, this behaves very similar to under acidic conditions, it behaves very similar to the bromonium and the mercurium ion. So it's basically history repeating itself there. Now, under basic conditions, epoxides, they attacked the least substituted carbon. So under basic conditions, you don't need to protonate that oxygen. We can attack it with, say, hydroxide, or even things like a Grignard reagent, so methyl minus. I'll just put it as in quotation marks. So this could be a Grignard, or a lithium, methyl lithium type thing. So under these conditions, it attacks the least substituted carbon on the opposite side. So let's go there, up. Either of those sort of reactions. So if we had a similar situation, and we were reacting with methyl magnesium bromide, our product would be, and we're going to star this methyl here. This methyl would be there. So we sort of did this all before, right? So the other part why this is a review is that with cyclic, particularly epoxides, they open up under acidic or basic conditions, but where the nucleophile attacks is reversed between the two of them. So under basic conditions, it attacks the least substituted carbon. Under acidic conditions, it attacks the most substituted carbon. So that's what's going on with epoxide. So if we right, so this would go an attack here. This would go up. Second step, we would add H plus to protonate that alcohol, and that would be our product. So, and it's relying on the ring strain of that three-membered ring to open up epoxide. So that's why they're relatively easy to open up. THF, for example, takes a lot of work to open that up, very specific conditions. So there's two really new reactions to talk about with regard to ethers. Two. And one of them is technically, we've seen it before actually. So if we have an ether like this, and we put it in a solution of HBr and water, and we're going to heat this up. And what is going to happen next? So we can basically put this together, and let's do another one here. Let's do this. Something similar. Let's put this with HCl and water and heat this up. Okay, so if we had to classify the ether as a Lewis acid or a Lewis base, what would we classify it as? Lewis base, right, because it has got these lone pairs that it can donate. And if we had to classify HBr or HCl as a Lewis acid or a Lewis base, we would classify those as acids, right? Because there's a polar bond to H, donates an H. So let's do these mechanisms here. So, and we're going to see that we've seen this sort of before. So this is going to attack there. Electrons are going to move on there. This is going to attack there. Electrons are going to move on to there. So we're going to have an intermediate that looks like this. Now I'm going to just draw this as a methyl group because it's going to help us out here. Okay, now we've got these two intermediates. The protonated ether, is that an electrophile or a nucleophile? Right, it's an electrophile. It's carrying a positive charge. And if you look at the bromide or the chloride, these are both Lewis bases because they've got some lone pairs they can donate. So what we're going to do now is that if you had this question here, and this was a substitution. So at the end of last term, when we were doing our SN1 and SN2 and all these sort of fun reactions, and if I was to put molecule A and ion B together and said, okay, do a substitution reaction here, what type of substitution reaction would you do? SN1, SN2, that sort of thing. Okay, so we've got, okay, so there's two basic possibilities here. We could have, so if this was an SN1 reaction, the way that this would work was that we would have to move these electrons here like this, right? To generate secondary carbocation and methanol. And then the bromine would come in and attack there. So our secondary alcohol, we couldn't do it the other way because the methyl with the positive charge is way too unstable. So how in the scheme of carbocation stability, where does from primary, secondary, and tertiary, which are the most stable carbocations? Tertiary, right. So this would be the most stable. This would be the least. and secondary is sort of in the middle. So so what we've got, our ether here, on one side is a secondary and on one side is a primary. Like we got a primary carbon and a secondary carbon. So in situations like this where this is going to favor an SN2 type mechanism. So instead of doing what I've drawn down here, this bromide is going to attack the methyl group, because remember, methyl groups are the fastest for SN2 reactions. And then these electrons will move on to here, and our product will be methyl bromide and our cyclohexanol. So this will be let's make our screen smaller. This will be an SN2 reaction. Because methyl groups, they're fast for SN2. Now, the example I've done right beneath this is exactly the opposite. So I'm going to, what am I going to do? Let me get rid of this part here. Let me just erase it. Well, everything seems to be glitchy. Okay, so, well, it's the perfect time for things to be glitchy because it's the end of the class, right? So what we'll do on Tuesday is finish off this little bit here. Oh, you're not doing anything right here. What we'll do is, so the new reactions basically for ethers is what we're talking about here is an acid catalyzed hydrolysis of, or acid catalyzed cleavage of ether. So this is what we'll finish off on Tuesday. The way that this works is that it's either going to be cleaved through an SN2 reaction or an SN1 reaction. So in that realm of things, we've sort of seen this before. We just have to do an analysis of our ether to see, will this be SN1 or will this be SN2? So so the first example here would be SN2. The second example we're going to do is going to be SN1. And then there's one other new reaction with the ethers that we're going to talk about. So, but besides that, we'll get to that on Tuesday. I don't know why yeah, and I'll talk about some other stuff on Tuesday. On Thursday's class, it'll basically be a review for the midterm. So it looks like we'll get done the ether part, and that's where we'll basically stop for the midterm. All right. I understand some of you have a midterm later today, so good luck if you do. And I'll see everybody on next Tuesday. There is an assignment, a short assignment due for synthesis. Take a look at that. And if you have any questions, just email me. All right.
Thank you.
You bet. Have a good day.